Learning Objective 11 is about limitations of direct map cache and techniques for improving it. In the first part, we see most common metrics for measuring performance of memory hierarchy. Then we discuss limitations of direct map cache and introduce a method called Set Associative Cache to improve hit rate of the cache. There are two main metrics for evaluating performance of memory hierarchy. First, we extend a classic CPU performance equation to account for memory stalls. Second, we develop a special metric for measuring performance of a memory hierarchy. This metric is called average memory access latency. This is a single number in unit of time and reports how long it takes to access, read or write data from the memory hierarchy on average. This is a very important metric since it gives us a meter to compare various memory hierarchies in particular and report improvements in numbers. Improvements we could consider for a memory hierarchy are twofolds: improving miss rate and or improving miss penalty. This learning objective focuses on improving miss rate, and the next one talks about improving miss penalty. We extend classic CPU performance equation to account for memory latency. In the original equation, we assumed memory was perfect, meaning it would never miss. We add the memory stall clock cycles term to the equation to account for imperfect memory. Memory stall clock cycles is a number of clock cycles CPU was waiting for the memory, and is calculated as rate of memory accesses multiplied by the miss rate of the cache multiplied by the miss penalty. This number is in unit of time ultimately. Let's see an example. Assume the miss rate of the data cache is 4%. If a processor has a CPI of 2 without memory stalls, meaning the perfect CPI of the processor, and the miss penalty is 100 clock cycles for all misses, determine how much faster a processor would run with a perfect cache that never missed. Assume the frequency of all loads and a store is 36%. The first thing we have to do, we have to calculate the CPU time of the perfect processor without any memory stalls. We use the classic CPU equation, and we don't have the total number of instructions. We keep that as a parameter, and eventually it will cancel out. And then multiply this by the CPI, the perfect CPI that is given, which is equal to 2, and multiply that by the clock cycle. We don't have the clock cycle time neither, so we keep that as a parameter as well. Then we calculate the CPU time for the case that memory exists and we have memory stalls. We calculate the memory stall cycles as the rate of memory accesses. So we have total instructions as I. 36% of instructions are load and store, so we multiply I by 0.36. And then we multiply this by 0.04, the miss rate of the cache, and multiply the whole term by 100, the miss penalty, the number of cycles it takes to handle the miss. Ultimately, the memory stall cycles will be equal to I multiplied by 1.44. This is the overhead. This is what perfect CPU has to pay in actual CPU. So we recalculate the CPU time, this time for the case that we don't have the perfect cache. In this case, we add 1.44 to the base or perfect CPI. And what we end up with is 3.44. And lastly, we calculate the improvements by dividing CPU time of the real case with the stalls over CPU time of the perfect without any stalls. So clock time and I will be canceled from both sides of the division here. And we end up with 3.44 over 2. And we end up with 1.77. That's the rate of improvement we get if we improve the memory hierarchy of this processor And that's the maximum amount of improvement. So any improvement we make will be less than 77%. Average memory access time is the second metric. It is the average time to access memory considering both hit and misses and the frequency of different accesses. It is a realistic metric that measures memory hierarchy performance directly. For a two-level memory hierarchy, it is defined as hit time plus miss rate multiplied by miss penalty. Miss penalty is very larger than hit time normally. And in a very good memory hierarchy, miss rate is very low. So the second term we see in here does not contribute much overall into average memory access time. Let's see an example. Find the average memory access time for a processor with 1 nanosecond clock cycle time and a miss penalty of 20 clock cycles, miss rate of 0.05 or 5%, and a cache hit time of 1 clock cycle. So if we replace these numbers into average memory access time, what we get ultimately is 1 nanosecond for hit time, plus 0.05 or 5% multiplied by 20 nanosecond of miss penalty, which the result of multiplication is also 1 nanosecond. So overall, average memory access time is 2 nanoseconds or 2 clock cycles. That's a very important metric that accounts for both hit and misses and is a typical number that we can use for comparison after we make any improvement to the memory hierarchy. Now that we have metrics for measuring performance of memory hierarchy, let's introduce techniques for improving direct map cache and measure improvement amounts. We discuss a miss rate improvement technique in this learning objective and leave the miss penalty improvement technique for the next learning objective. As we discussed earlier, one major drawback of direct map is that memory lines are mapped into the same cache location based on their address. This is also known as cache contention. As an example on the right, there is no way to have all gray lines in the cache at the same time because they are mapped to the same location. This poor mapping causes 100% miss rate if an application needs gray lines only. And remember, this is not related to the size of the cache. This is only because direct map is mapping the gray lines to the same cache location. So even infinite cache size cannot resolve this issue. In the next coming few slides, we discuss a technique to address this shortcoming and improve miss rate of direct map cache. This technique is called associative cache. Let's compare associative cache to direct map. When searching a block in a direct map cache, there is only one possible spot in the cache for the block to be. If the line is there, that's a hit, otherwise that's a miss. With associative caches, we have more than one spot in the cache, and we have a set of spots. In a fully associative cache, the block may be in any location in the cache. Searching this cache requires n comparisons, where n is the size of the cache. While this completely removes cache contention, again, contention, the chance of two blocks being mapped to the same cache location, it is super expensive for the hardware to implement for large caches. A trade-off in between fully associative and direct map is called set associative. Set associative has few sets that work like direct map, and within every set, there are multiple choices. And within every set, we work like fully associative. Looking up the cache using set associative is done in 2 steps. First step, we find the set that memory block is mapped to. In the second step, we search all the blocks in the set for a tag matching the address. The number of blocks in the set is called ways. And for example, if there are 2 lines in the set, it is called two-way set associative cache. Let's see all flavors. One-way set associative is the case where there is only one entry in the set. This is a special case, and it's equivalent to direct map cache. Two-way set associative is the case where every set has 2 lines. Our data might be in any of the 2 ways. Similarly, there is 4-way set associative. Data might be in any of the 4 ways within the set. And when all the lines are in one set and there is only one set in the cache, this special case is called fully associative. In this case, any entry in the cache might have the data that we are looking for. How all that impacts miss rate? That's actually very effective. Every line in the chart shows the miss rate under various number of ways for one particular cache size. For example, the gray line for 1 kilobyte cache, the trend suggests that 8-way associative cache can reduce miss rate by 4% compared to direct map or one-way. And this is quite significant. Although the impact on large caches is small, you might be wondering why. This is because large caches already have too many lines and contention. The direct map drawback is already low in large caches. Again, remember, set associative cache aims to improve when suffering from contention, and this is not much the case in large caches. Okay, let's see an example of a sequence of memory requests on various caches and understand how set associative cache works. First example is the direct mapping. Suppose this sequence of requests sent to the cache over the time, memory address 0, 8, 0, 6, and 8. First thing we have to do to run the trace on the cache is to find where every one of these addresses are mapped to for this particular cache. So for the direct map, that's pretty straightforward. We get the remainder of the address by the number of lines in the cache. And the result defines the set that this address is being mapped to. The calculation here shows every index every index or cache block that address being mapped to. So first 3 addresses are mapped to index 0, entry 0 of the cache. Address 6 is mapped to entry 2, and address 8 again is mapped to entry 0. This is how we represent our cache, 4 lines in the cache. Let's start the trace. We have the first request. We send the first request to the cache. There is no data in the cache, so that's definitely a miss. We bring in the data, and since this address corresponds to index 0 of the cache, this data should sit at index 0 in the cache. Then we go to the next request. Next request is for address 8. Address 8 is mapped to index 0. At index 0, we have memory address 0, not address 8. So again, that's a miss. And we have to bring the data into the cache, and we have to replace mem0, which is already in the cache. We do so, and then we go to the next request. Next request is again for address 0, but we have just replaced address 0. This example is also showing how contention happens. Address 0 and 8 are constantly replacing each other. Address 0 is mapped to index 0 of the cache. At index 0, we have memory address 8, so we don't have 0, so it's again another miss. We go to lower level memory, get the data, and bring this and replace it at index 0. Then we go to the next request, memory address 6, mapped to cache index 2. At index 2 of the cache, we don't have any data, so that's definitely another miss. Then we go get the data, bring in the data, and store at index 2. And the last request for address 8 maps to index 0. At index 0, we have memory address 0. So our data is not in the cache. That's again another miss. We go get the data, bring it into the cache, and replace it at index 0. So in the case of direct map, among the 5 requests, we have 5 misses, and miss rate is calculated as 100%. Second example is two-way set associative cache. Assume the same sequence of addresses. Let's calculate the set ID this time. Here our cache configuration is different. We have 2 sets, and in every set we have 2 ways. In total, we still have 4 blocks in the cache, but they are organized as 2 sets, 2-way per set. The way we calculate the set ID is very similar to the way we do for direct map, but instead of getting the remainder by total number of blocks, we get the remainder by number of sets. We have 2 sets and we get the remainder by 2. As we can see, all the blocks are mapped into cache index 0. This is how we represent our set associative cache in this example. There are 2 blocks with the same set. We have the choice to select where we want to keep our data. And within the set, we have to be fully associative. Let's start the trace by sending address 0. There is address 0 that is mapped to set 0. At set 0 of cache, there are 2 lines. None of the lines have any data. So that's definitely a miss. We go to lower level and get the data, and we bring it into the cache. We can store in either of the locations in set 0. Then we go to the next request, address 8. Address 8 is mapped to set 0. In set 0, we have memory address 0 and 1 empty spot. We don't have address 8. So that's again another miss. We go get the data, but this time we don't need to throw out memory 0. We can keep memory 0 and use the other way of set 0 for keeping address 8. Then we go to the next request. Next request is for address 0. Address 0 is mapped to set 0, and in set 0 we have memory 0. And this time this is a hit, and we get the data from the cache. Then we go to the next request, memory address 6 mapped to set 0. At set 0, we have address 0 and 8. We don't have 6, so that is a miss. And we have to get this data from lower level memory. We go get the data and we replace either of the lines in set 0. We will discuss replacement policies. Some replacement policies are smart and find which line is not being used often or haven't been used for a long time. There are different policies we'll discuss, but for now, assume we just replace memory address 8, which is the block that hasn't been used recently. And we put memory address 6 at this location. Then we go for the next request for address 8. Address 8 is the block that we just replaced. At set 0, we don't have memory 8 again. And that is also a miss. We get the line and we bring it into the cache, and this time we replace with memory 0 because that's the line that we haven't accessed recently. So with two-way set associative, a little bit of improvement. Miss rate is 80% instead of 100%. Third and last example is fully associative cache with the same size. We assume the same sequence. This time we only have one set in the cache. All the lines are options. We have to search all the lines for finding our data. There is only one set in this case, and this set has 4 ways. So we basically get the remainder by 1, because there's only one set, and all the sets are mapped to same set. All the addresses are mapped to the same set. We start with the first request. It's not in the cache, that's a miss. We bring it and we can store in any of the 4 locations available in the cache. Then we go to the second request, address 8. It's not in the cache. We bring it in and we store in one of the empty spots which is available. Then we go to the next request. That's for memory address 0. It's already in the cache. That is a hit. We return from the cache. And then we go to the next request. Memory address 6, that's not in the cache. That is a miss. We get the data from lower level, store in the cache. Then we go to the next request, memory address 8. Data is in the cache, and that is a hit. So again, this is a little bit more improvement over two-way associative. And this time, instead of 80% miss rate, we're getting 60% miss rate. More ways we get for our cache, less contention for the cache. Let's see how we can search a block in Set Associative Cache. Similar to direct map, address bits are divided into tag, index, and byte offset fields. Set Associative Cache is effectively composed of n direct map caches, where n is the number of ways. In this example, n is 4. And we see a 4-way set associative cache. So we see 4 subcaches. We call every one of the direct map caches here a way. For the lookup, index field is sent to all ways. So we see 8-bit of index is sent to all the 4 ways we see in this example. There is only one entry in every way, as the way itself is a direct map cache. Then we compare the tag of all ways. If on any of the ways we find tag matches and v bit or valid bit is set, that is a hit. This is what the OR gate at the bottom does. In this case, cache sends the corresponding line from the way that responded with hit to the processor. Here are the formulas we had for direct map, refreshed for set associative. This is how to calculate the size of the tag. Red highlights show what is new here, and ways is the only new thing here compared to the formulas for direct map. Ways impact number of index bits, and from there tag bits are impacted. There is no change to the way we calculate byte offsets.